Okay, hi everyone. Welcome to our weekly meeting today. So I think we have three presenters today, and that is Robin, me, and Natalie. So Robin, would you like to go first?
Yeah, sure. So I will begin to share my screen. Can you see it?
No. Yeah.
Okay. Yeah, so in last week I briefly talked about the reinforced learning, but I missed an important concept about it, that's the policy. So I will briefly talk about it today. So policy decides which action is selected by the agent as on state, and two criteria can be used to classify policies. First, depending on whether policy is time-dependent or not, we can categorize them as either stationary or non-stationary. So stationary means that it is time-independent, and non-stationary means that it depends on the time. And if the cumulative rewards the agent's aims to optimize are limited to a finite number of future steps, we could use non-stationary policy. But in most cases, we will use the stationary policy. So stationary policy is like something like this, like like this formula we talked about last week. So either whether it is t plus 1 or t doesn't matter, as long as the state is the same, the reward or something is the same. And second, policy can also be categorized under the criteria of being either deterministic or stochastic. In a deterministic case, what action will be taken at a certain state is determined. But in a stochastic case, given the action and the state, the policy will return the probability that action A might be chosen in state S. So it is not determined by some probability function we will get. In last week, we also talk about some limitation of the reinforced learning and talk about some deep reinforced learning may help to solve this. So in this week, we will shift to the deep reinforced learning part. So deep reinforced learning make use of deep learning and reinforced learning. We will create a sequential reinforced learning process in which deep learning determines the action taken at every stage. So we can categorize our deep reinforced learning method into basically two categories. If we use either value function or policy to act on the environment, the method is called a model-free reinforced learning, this part. And it can be further categorized into two branches. One is a value-based method and another is a policy-based method. And if we make use of the models of the environment, it is referred to as the model-based reinforced learning, this part. And it is the general schema of the deep reinforced learning method. Here we have some function, which is the deep learning part. We will use some convolutions or recurrent cells to calculate our values or something. And here we have our learning algorithm, which is the category we discussed before, like the value-based reinforced learning or something else. And we also have some controller, which is some phases or hyperparameter management. And in the reinforced learning, we will have our agents interact with our environment. And this replay memory and policy act like a bridges between these two components. So replay memory will it's like some feedback you get from the environment. The agent can learn from it about its previous memory, so it can help to speed up the training part. And I will also briefly talk about the value-based method for deep reinforced learning. The value-based class of the algorithm aims to build a value function, which subsequently led us to define a policy. And most frequently, we will use an algorithm including Q-learnings and deep Q-learning. And here we will use the deep Q-learning as an example to understand what value function means. Like one value function we frequently use in value-based method is the action value function, QSA, which represents the total value of taking action A in stage S. It is the sum of the future rewards R adjusted by the discounted factor gamma. So our goal is to optimize this value function. We are given the stage S at T and the action taken at A, and we want to get a policy that can maximize this formula's expectation. And the basic step of deep Q-learning algorithm is as follows. We will train our convolutional neural network to extract the essential features that can help the agents to make the decision. And we will calculate the Q value of each possible action, and we will perform the back propagation to build the most accurate Q value. So the model is like simplified in this graph. We have some stages, we will forward it to our neural network, and we will output some Q value, and we will like do the backward and to like help to get the most accurate values here. So the benefit of using value-based method is like similar benefits for any method in the model-free method category. So we don't need to have a model for the Markov decision process to perform this method. Because like in Q-learning, the optimal policy is given by this formula. We only like need to get S and A and nothing else we need to know. Yeah, so it is like all about my presentations today. Is anyone have questions? Okay, I will stop sharing.
Okay, thanks Robin for introduction about the value-based method in deep reinforcement learning. So yeah, next I will present about the policy-based deep reinforcement learning and also the model-based one. So just a quick recap. I will introduce the second model-free method, which is the policy-based method. So policy-based methods learn the policy function directly without calculating a value function for each action. These methods use a learning signal derived from sampling instantiations of policy parameters, and a set of policies is developed towards policies that achieve better returns. An example of a policy-based algorithm is policy gradient method. Before I introduce the policy gradient method, I'd like to first explain the difference between the value-based method and policy-based method, and to show why we need a policy-based method. So in the value-based method, as Robin has just introduced, we calculate the Q values for all possible actions in the action space. But in real world, the number of actions can be a lot or can't be imaginable. For example, the robot walking problem has continuous and high-dimensional action space. So in policy-based methods, we directly learn our policy function pi without worrying about the value function, which means we can choose actions without calculate the Q values. So next, I will introduce the policy gradient method. In policy gradient, we directly learn the policy function pi, which gives the probability distribution of actions. So you can see here that pi SA is mapped to some number between 0 and 1, and it means the probability of taking action A given state S. And the parameter theta is the parameters for the policy function pi. So neural networks can be used to find the policy function. The network takes the state as an input and produces the probability distribution of actions. So here's the process in simple terms. So first, the network will take the state as take in a state and get the probability of each function. And then it will select the most probable action and observe the next state and the reward. And it will repeat until the end of the game and evaluates the total rewards. So based on the rewards and using backpropagation, the parameters theta in the network can be updated. In this way, the network allows the agent to play freely, but with every successive game, it provides better probabilities for actions that will lead the agent to a positive result. So I will show some math behind it with the objective functions and the gradient. So what we want to maximize is the rewards based on parameters theta. So we can use the expected return of policy pi starting from a given state S0 as the objective function. So here is the equation for the expected return of policy pi. So first it sums over the states where the rho pi s is the discounted state distribution. It means the probability of being at state S when following policy pi and can be calculated with this equation here. So you can see that to calculate a rho, we sum over all the time step t and with the probability of being at state S at time step t multiplied by the discounted parameter gamma to the power of t. So then for the latter terms here, pi SA is the policy we want to learn, while for the R tilde SA, it is equal to the sum over all the S tilde in all the states with the transition probability times the reward of taking action A at step S, while the next state will be S tilde. Okay, so here is the function that we want to maximize. And according to the policy gradient theorem, I will not introduce this theorem today, but later we can, if you're interested, you can make more research in this direction. According to policy gradient theorem, the gradient of the objective function is proportional to the equation at the right-hand side. So for the former part, it is still the same as the equation we already have. And here is sum over all the actions A with the product of these two terms. The first one is the gradient of pi gives S and theta, and the simplest way to estimate it is to use a score function gradient estimator, because this term can be estimated in this way. You can see that we multiply and divide by the policy function. And then we can estimate it with the value of the policy function times the log derivative of the function, which is the score function. And for the latter term, it is the action value function under pi. Actually, it is the Q value, so we don't want to calculate it, and we want to estimate it. And a simplest way is to use the cumulative return from the entire trajectories. So next, I will show a naive algorithm based on the two simplest way estimators. So that is the reinforced algorithm and also called the Monte Carlo policy gradient. This algorithm uses Monte Carlo to create episodes according to the policy pi, and then for each episode it iterates over the states of the episode and computes the total return. Then it uses the return and also the score function to backpropagate and learn the parameter theta. So here is the pseudocode for the algorithm. The input is a differentiable policy pi, and the step size alpha, which is a positive number, is the algorithm parameter. At the very beginning of the algorithm, we will initiate the policy parameter theta. For example, we can initiate it to 0. And then you can loop as long as you want. And in each loop, you will generate an episode. That is the state, action, and reward going through the time steps, following the policy pi. And then you will loop for each step of the episode, like for each time step, yeah. And you will first calculate the return from step t as g, and then you will update the parameter theta, and alpha is the step size, while gamma t is the discounted parameter at step t, g is the return, and here is the score function. So doing this way, you will train a policy that can give the positive result. Is there any questions so far? Sure. So, so next I will introduce the model-based method. So for the value-based method and policy-based method, we don't interact with the model of the environment. However, if we make use of the model of the environment, that is called the model-based method. So when a model of the environment is available, we can use the model as a proxy for the actual environment. So the model can be the estimated transition function and the estimated reward function. So here are two simple examples of the model. In many games, the rule of the game is the model. And in other cases, it can be the law of physics. And sometimes we know how to model it and build simulators for it. We can define this model with rules or equations, or we can use Gaussian process, Gaussian mixture model, or deep networks. To fit these models, we run a controller to collect sample trajectories and train the models with supervised learning. So then I will show how we can learn a model. In model-based reinforcement learning, the model may be known or learned. So if you want to learn it, here is the steps we can run to learn a model. So in step 1, we run a base policy. It can be a random or any educated policy. And then we can observe the trajectory here and save that in the set D. In step 2, we use supervised learning to train a model, FSA, which can minimize the least square error from the sampled trajectory. And in step 3, we will backpropagate through the model we have just learned into the policy to optimize the policy pi. And to be more detailed in this step, we can use the model to predict the next state given an action. Then we use the policy to decide the next action. And with the state and actions, we can compute the cost. Finally, we backpropagate the cost to train the policy. So now we have also an updated policy. We will run it and add the resulting data, like more observations of the trajectory to the set D. And after that, we will repeat from step 2 and loop through step 2 to step 4. Like we continue sample and feed the model as we move along the path. So that is the overall structure of how a model-based method works. So here is a comparison between model-free and model-based methods. The respective strengths for the model-free versus model-based approaches depend on different factors. So first, the best suited approach depends on whether the agent has access to a model of the environment. If that's not the case, the learned model usually has some inaccuracies that should be taken into account. So then the model-free method may be more preferred when the model environment is not available. Second, a model-based approach requires working in conjunction with a planning algorithm or controller, which is often computationally demanding. And time constraints for computing the policy pi needs to be taken into account. Third, for some tasks, the structure of the policy or value function is the easiest one to learn. However, for other tasks, the model of the environment may be learned more efficiently due to the particular structure of the task. Thus, which one performs better depends on the structure of the model, policy, and value function. Okay, so that's all for my part today. Is there any questions? Sure, then I will stop the presentation. So I think, yeah.
Yeah, I will start now sharing my screen.
Yeah.
I have a question for both of you. Have you looked at the applications of deep reinforcement learning? Do we have any notes about the applications, like use cases?
We haven't add notes for that part.
Like there are specific scenarios where reinforcement deep learning is extremely helpful, but we cannot use it everywhere. So it's important to learn where we should apply it, like the specific use cases.
Sure. We can cover that part in the next meetings, I think. Yeah.
Thank you.
Okay. Nali.
Okay, I will start. So today I'm going to talk about variational autoencoders. And this is one of the most fundamental architectures for generative modeling, and it was created in 2013. Before I will move to variational autoencoders, firstly I would like to talk about autoencoders. So autoencoders consist of the two major parts, which are encoder and the decoder. So encoders try to compress high-dimensional input data into lower one, while decoder tries to decompress representational vector to the original domain. And here I have the image which explains this process. So we have this original input data. In this particular case, it is digit 6, and we pass it to autoencoder. Then encoder compress this high-dimensional input data into lower one, and then we have this representational vector, and then we reconstruct and get this as an output. So
I have a quick question for you.
Yeah.
How is that process different from the adding the convolutional layers? Like you can add a similar convolutional layer to get the similar output, right?
Yeah, I don't get exactly what do you mean. Similar output. Do you mean representational? I don't. This one. I don't understand.
So my
In
quick question here is, can you explain a little bit about the dimensions of the input image and output image? Are they in the same dimensions, or it is reducing the dimensions?
In case of encoder, I mean, I would explain it because I have this sample code for it. I mean, encoder, it looks very similar for what we have in convolutional neural network. But in case of decoder, we have this mirror case that we have in convolutional neural networks, and we are trying to reconstruct the image, from the output that we get from the encoder.
Thank you.
Was it clear, or I don't know?
Yeah, thank you.
Okay. So AutoEncoders try to train the network so that the weight for the encoder and decoder make the loss between the original data and its reconstruction as small as it's possible. And here I have the sample code for the encoder. And as I already talked about, here we have this convolution layers, and then we have this activation function and batch normalization and dropout regularization. Then we flatten it, and that's it. And you can also check this code yourself. And in case of the decoder, so decoder, as I already said, is a mirror image of the encoder. And here, instead of convolutional layers, we use convolutional transpose layers, as this is shown in the code here. Actually, it is not necessary for the decoder to be exact mirror image of the encoder, but it is inevitable for the decoder to have exactly same size for the output image as the input size of the decoder.
You just completely answered my question. Thank you.
And right now I would explain what are these convolutional transpose layers. So in standard convolutional layers, if we have this try2, then we have both the height and both the width of the input tensor. And convolutional transpose layers have a kind of similar functionality, but we are doing something which is vice versa. I mean, if we would have here try2, then we would double both width and height. And as I showed to you, this con2d transpose function is implemented already in Keras, and this implements this functionality, which I described here. And here is the code that puts all of these together. So in order to have full autoencoder, we need to combine this encoder, model and decoder network, and finally we would have our autoencoder. But autoencoders are not very great. They have several problems, like sampling for latent space can be very problematic. With autoencoders, it is not guaranteed that we would obtain the same quality when sampling from latent space. To give you an example, suppose that we have this standard amino acid dataset where we have these digits, and for instance, autoencoders manage to learn, how to generate or reconstruct the digit 6, but they might not be able to perform well in case if we have digit 9. So this is what this means. And also some generated outputs are poorly formed. In order to solve these problems, variational autoencoders would help us. And firstly, I would describe the difference between these two in case of encoder structure. So in our autoencoder, each image is simply mapped to one point in the latent space, while in variational autoencoder, each image is mapped to multivariate normal distribution around that point. And here you can see this in this image. So this is just autoencoder mapping to the single point, and here to around some normal distribution to that point. I would now briefly describe variational autoencoder-encoder. So if you have mu, mean, and symmetric covariance C in 2D, they are defined as follows. So you can see it here. And in variational autoencoder, we assume that we don't have correlation between these two dimensions. So this simplifies this process. So the encoder needs to map each input to mean and variance vectors. And as a result, we would have these two vectors, mu the mean point distribution and log var the logarithm of the variance of each dimensions. And in order to encode our images, we will use this formula. Right now, I'll describe how this modification helps. So for the autoencoder, latent space doesn't have to be continuous. Here we are sampling an area near mu, and decoder will try to ensure that points in the same neighborhood generate similar images. So we would reduce our reconstruction loss. And I also provided a simple code for variational autoencoder-encoder. And as you can see, we have here these changes, apply this self mu and self log var, and also here this sampling. It differs from the standard autoencoder-encoder structure. Right now, I would describe the loss function, which is also different from what we have in autoencoder. So in ordinary autoencoder, we might use root mean squared error. It is not a must, but most frequently this loss function is used. And in case of variational autoencoder, we also have an additional component like Kullback labeler divergence. So what is this Kullback labeler divergence? It is used to estimate the difference between two probabilities. And here we want to measure the difference between our normal distribution with mu and log var parameters and standard normal distribution. And here we have this formula in order to measure our Kullback labeler divergence loss. And the sum is taken from every dimension from the latent space. And in order to minimize our loss, the ideal situation would be to have 0, which would be achievable in case if we have mu and log var equal to zeros. Right now, I will describe how this function helps. So it helps to have a well-defined distribution, and it also reduces the probability of gap formation between point clusters. And I would also want to add that in loss function, we just simply add reconstruction and Kullback divergence losses. And additionally, we need to weight this reconstruction loss by some factor, and this is very important because if we would poorly choose this weight term, then we will get unsatisfactory results, like in autoencoder. And I also have a sample code for this loss function, and as you see here, we implement this root mean squared error here, and then we have this Kullback labeler divergence loss here implemented, and then we finally add these losses and apply them to our model. That was all that I wanted to talk about today. I hope it was interesting.
That was very interesting, but I have some comments for you. So like in terms of these nodes that you have like loss function or loss function code, so that is very general. It's not a good idea to use like general terms in titles of nodes, because can you click on the left sidebar? Can you click the search button?
Here?
Yeah.
Mm.
So if you search loss function,
Yeah, I understand what you mean.
so loss function can be applied to everywhere. Like, how should I know you're talking about loss function for autoencoder? You see my point?
Yeah, I would modify these notes.
Yeah,
Thank you.
it will be great if you just modify the node titles and make them specific.
Yes.
And another suggestion is for nodes that you're just putting piece of code. You can do two things to improve the node. One is please use code type for the node so that everybody, when they want to open it, they know that there's a piece of code, right?
Oh, thank you. Thank you.
And one more thing. So for this code, piece of code, loss function code, can you click the pencil button?
Do you mean this?
Right. Click edit, please.
Okay.
Edit or improve the node. Yeah. So what you can do is enter a new line on top of the code, on very top.
Here?
Yeah.
Or yeah.
Yeah. So on very top of the code, enter 3 backticks. So you see the tilde button on top left corner of your keyboard, the tilde button. So if you use shift and press that button, it would print tilde.
This one?
Otherwise, it would print backtick, right? 3 backticks. So add 3 backticks and then write Python.
Okay.
Without a space, you don't need to close it. You don't need to have a space between backticks and Python. And lowercase p. I think both lowercase and uppercase work. So can you get rid of that space? Yeah, get rid of that the space, please.
I'm sorry. What should I do?
After the 3 backticks, there is a space. Just remove that space. Yeah.
Okay.
And at the end of your code, so close the block using 3 backticks. Yeah. Do you have a space before the backticks on the first line? Like
what do you mean?
Before.
Before? Yeah, I think I have.
So get rid of that. Yeah. And you don't need to have any space at the end of Python. Like after Python, there should be any spaces. Just 3 backticks, Python, and at the end of your code, close 3 backticks. So if you click that, you need a square root of x, like a little bit on top of your mouse. Yeah. So you see what it does?
Yeah.
So it identifies that there is Python code, so it highlights your code.
Yes.
Right.
Thank you.
So that's easier to read. Right. And so if you save this right now, just click propose button. So that should do a similar thing. You see that?
Yeah.
Good. And one last thing. So I was going through your notes. Many of them don't have any citations. Like when you summarize a paper, a book chapter or something, you need to cite it so that if I want to learn more about what you're talking about, I should be able to look at the citation. You see, like there is a tag, data science, but the references section is empty.
Yes. Okay, I understand. I think I would add parent notes because I have included references sometimes, but I have not included them as a parent notes. I think I should add them as
Thank
parent
you.
notes.
Yeah, that would be very helpful for anyone who wants to follow up with the notes you have added.
Thank you a lot. That helped me to understand my mistakes.
No mistakes. You're doing a good job. Thank you.
Okay, thanks, Nani, for giving us introduction of the autoencoder and decoder. And thanks, Iman.
And I have additional, could you suggest me some introductory book for deep reinforcement learning, because I'm very new at this area?
Sure. Maybe you can refer to my reference of the node I have proposed.
Okay.
Yeah.
Thank you.
And just to confirm, is there anyone who would like to make presentation today? Anyone else? Okay, so I'd like to make an announcement is that since actually we have already been going beyond the Coursera specialization and the textbook, and actually now I think we are moving gradually towards the research part, and we will maybe start with the research papers very soon. So I think I would like to make the meeting next week as our last meeting in the big group. And after that, we will dismiss and form a small research group and move on. So if you'd like to enter the small research group, you can just indicate your research preference at the table in the end of our detailed research plan. If you write your name there, I know that you'd like to join the small research group.
Is there any requirement for a small research group?
Yes. To determine who will join our group, I will just looking at the quality and quantity of the presentations you have made. We have the records of presentations sheet, and we also have the recordings of every meeting we have held. So based on that, I think that is a good indicator of how active you are and how many time you are willing and able to devote to our research. So that will be the thing that I will make decisions based on. Yeah.
Will next meeting also, we will present on next meeting also, right?
Yes.
Yeah.
So I think the question was twofolded in terms of requirement. So one question may be, what if I don't want to work on any of the research projects? Is it possible for me to continue just presenting, summarizing what I learned and present in the meetings? And the second question would be, I think what you answered, that if I want to participate in any of the research projects, is there any requirement that I have to satisfy to be able to participate?
For the first question, I think we need to I think we need to decide which paper idea we will work on together, and after that, I think all the discussions will be around the specific idea and the field related to that idea. So I think if someone don't want to work on an research but still want to learn more things in deep learning, maybe the research group is not a good place to. Yeah, I think research is like go deep in one specific field rather than explore more possible concepts in the deep learning field. How do you think, Iman?
Yeah, sure.
Yeah. So what's the second question?
So I think you already answered the second question
yeah.
before my question. So the second question was, if I want to join any of the research focuses, like research projects, what is the requirement for that? And you mentioned we should have presented during the previous meetings, and you will look at the number of nodes and quality of nodes and presentations. in previous meetings.
Sure.
Also, I saw a document there in a Microsoft Teams about like let me find it. It was requirements to start reviewing.
Oh yeah, that one. I think I have make an annotation that it is no longer. Yeah, please forgot about this since
Okay. I see.
we don't have a solid threshold to determine whether you are enrolled. Yeah.
So we already have a couple of research ideas in the detailed research plan. It is not as detailed, but it is actually, it has like rough research plans for multiple projects. So if you have any other ideas, like research ideas that you like to propose so that others learn about it, and if they like, they can collaborate with you, please add it to that document. If you want to work on any of those research projects, you can also add your name and indicate your preferences on what research projects you want to work on.
Yeah. So after we have formed a small group, I think we can first decide which paper idea to work on. Yeah, and based on the pool we have now, I think the probability to work on the third one is really high. And if you're also free to change your preference if you find something more interesting. Yeah.
I just have also one question. So what would be the maximum amount of students for that small group?
Pardon?
What would be the maximum amount of students for that small group?
No,
Like
there's
how many
no.
students can participate in each group?
I would expect like 6 to 7, I think.
Great. And I also already wrote some notes for one research papers and
Would you like to share today or maybe next week?
maybe next week. But
Okay.
I saw that it would be difficult to follow those notes because like when it's about like formulas and too much I mean, it's such stuff that it would be better to read ourselves. I have my own preference like this. I don't know what would you like to do about that.
Sure. You think these papers are hard to follow?
I don't mean that exactly,
Yeah.
but it would be difficult to. I mean, when you're representing papers, it is difficult for others to listen because I sometimes can't catch up. Like even today, when you were presenting, I sometimes get lost and I need to review these notes myself.
Why don't you ask questions? That is something that I hear a lot, especially in like courses that I teach on advanced topics, and that is always my response. Why don't you ask questions? Like right now, today, you have a lot of time left in this meeting. That means during the presentations, you could ask a lot of questions. Even right now, if you have any questions, please ask. Like if there is anything confusing for you, the presenters are still in the meeting, you can ask.
I mean, I think I should read it. I mean, I just have that.
That's fine. No worries.
Yeah, actually, for the deep reinforcement learning, I also think that it is challenging when I'm preparing for that. And but I think what I present today, they are all based on something we have already covered or already learned, and so maybe just need more time to consume all these new concepts. Like
Yes,
So I have a quick, yeah, go ahead.
no, I just wanted to agree with her.
I have a quick question. So I just looked at the document for the detailed research plan document. So how many people have not mentioned their preferences yet?
I think most of us have mentioned.
So in that case, because we still have time in this meeting, why can't we just start planning for the third project?
Oh, yeah. Yeah, yeah, we can.
Yeah,
So,
I feel like there is no reason to postpone it to next week.
yeah, so how do you think we can like
So
the paper, which paper to review, or
no, first of all, we should think about a project plan. We should think about what we can do about this, and then I have already, in terms of the third project, I have already listed multiple papers here, so we can start working on these papers and we can start presenting them next week. What do you think?
yes, I just want to like a buffer time between the two phases, since seems that someone is still working on some presentations, maybe not really related to the uh the the research, but
Sure.
they still, yeah.
Sure, whatever you prefer.
Or I can just make sure that is anyone doing some working on some presentation not really related to research, but you still want to share with us?
I was working on transformers. I guess might be related because like it was TM, right? Use.
Right, that is a very important topic, actually.
And also, it's not related. I was working on guns. I'm not sure actually.
On what?
General adversarial networks.
Got it.
Yeah, but the general adversarial networks are not related. But it's a very fun topic.
Yeah.
I'm also.
So I have a proposal. Sorry, Aryan, you can continue. If you have something to say, you can continue, and then after you, I'll say what I wanted to.
Okay.
Yeah, go ahead, please.
Yeah, I'm also. I'm still preparing, but if next week is our last meeting, I'm going to be presenting too. So.
Sure.
Yeah, so or my suggestion is that maybe at the same time everyone can look more about the third one, and so we can also, after the presentation next week, we can discuss about our paper idea, our third paper idea.
Is it okay with you if I give you a little bit of a starting point? Like
Sure.
just food for thought during the week, so that each of us can start thinking about the problem, trying to formulate it. And when we start the research from next week, we have a better idea of what we are going to do.
Sure, that could be helpful, yeah.
So as I've written in the document, we have a fairly large data set right now of a student's usage of a practice tool. This practice tool is a spaced interleave practice tool. It is a retrieval practice tool, meaning that, so it is all about Python programming. As a student in this class, I answer questions using this practice tool. There are a lot of multiple choice questions. There are programming questions. We call them active code windows, that the student enters a piece of code. There is an online interpreter that interprets their code and returns immediate feedback. It shows the output. It actually runs their Python code in the browser. It shows them the output, or it shows them error messages, like debugging messages. And then, so the student, oh, give me a sec, please, sorry. Okay, so, and the student can try as many times as possible. As many times as they like. Like they can answer a question 10 times and see the feedback and try again, and see the feedback and try again. That's totally fine. So although in terms of multiple choice questions, they may see, so they may try like every possible option, and then they see the feedback and then they submit. That is totally fine, because behind the scene, the algorithm, again, the algorithm has nothing to do with machine learning. It's just a set of rules based on, it is a well-used space repetition algorithm called Super Memo 2, which is rule-based. So it looks at, so we modified that Super Memo 2 algorithm to do multiple things. For example, it monitors how much time the student spent answering each question. It monitors how many times they tried. They received feedback and they modified their answer, they tried again. It monitors how many pages of the textbook they looked at, and the correctness of the answer they submitted at the end of the day, right? These 4 different things. Also, we have another variable for who this student is, another variable for which question they're answering. We have 2 other variables for the section, like chapter of the textbook where this question is coming from, and subsection, like part of that chapter. What else do we have? We have, and of course, we have their history of answers over time. So the 9th variable in this set would be time, like time of answering. So a student may answer the same question multiple times. And so currently, the modified Super Memo algorithm that we have on the platform is basically taking subsections, like topics under its section, as a specific topic, meaning that instead of considering like flashcards for timing of when to answer each question on each flashcard, it considers each topic as a unit of the spacing, or as a unit of practice. Meaning that today I answered a question about this specific topic, like let's say deep reinforcement learning, right? So this is the chapter. Now, under deep reinforcement learning, I'm talking about a specific problem, right? Now, in that problem, in that topic, there are multiple questions, right? Now, the system asked me a question. I correctly answer that question. So the system believes I have learned that topic. It doesn't ask me until tomorrow. But tomorrow, when it returns to that topic to ask me a question, it doesn't ask me the same question if there are multiple questions under that topic. I'm not talking about the chapter, under that specific subsection of the chapter, like under that specific topic. If there are multiple choice questions, it uses round robin. Like it asks the next question, like a random question from that topic, right? If I answer it correctly, it doesn't ask me again until 2 days. If I answer it correctly after 2 days, it doesn't ask me until 4 days, and so on. Now, there is a very simple algorithm, like a very simple formula. Now, what if I answer it wrong? If I answer it wrong, it is going to ask me the same day another random question, or the same question if there is only one question from the same topic, right? So it asks me again and again over time, like with some questions and from other topics in between, until it makes sure I've learned it today. And then it asks me tomorrow. And if I answer it wrong, again, it asks me again and again tomorrow if I'm answering wrong, so the day after tomorrow, and so on. And if I answer it correct, so it spaces out the duration of not asking a question from that topic. So this simple tool has been so helpful for these students who are doing introductory Python programming that we, through multiple experiments, we show that it significantly increased the students' grades. For every hour of usage of this practice tool, their final exam grade on average increases by 1.04%, which is a huge effect. And we, in the same regression model, we looked at the effect of hours of studying the textbook, because we monitor whatever they are doing. And the hours of studying the textbook didn't have any significant effect, because it was crowded out by the effect of this practice tool. Now, the question is, if such a thing is so helpful, and one more thing before I continue. So because of the success of this tool that I built in 2000, I think 18, yeah, 18 was the first year we used it. Because of the success of the tool and our follow-up publication, the Runestone platform, which is the big open source platform that I developed this practice tool inside that platform, that received a lot of demand from many instructors in the US. Right now, more than 1,700 instructors in the US who are teaching Python and Java programming in different schools, like universities, high schools, who use Runestone, they also use the practice tool that I built. So, and all the data will be available to us soon, right? Not right now, but soon. But for now, we have a large data set of the variables that I just explained to you for every semester, every time they try to answer a question, for only our Python programming course, in which every semester we have about 200 students. So starting from like winter 2018, for every semester we have the data ready. It is like 5 semesters until now, I think, 5 or 6 semesters. And we can basically start analyzing that. We can start trying to develop some model to learn that. But developing such a model requires a lot of thinking and planning. It's not going to be an easy job. And here is the problem. The first problem is that we are dealing with a time variable. A student's answer to the same question changes over time. If I answer this question correctly today, it doesn't mean that I'm going to answer it correctly tomorrow. That is one problem. This problem is already addressed in some of these publications that I've shared on the document. So if you go through these documents, you'll see they're talking about such things. However, there is another problem that is very new to the literature. I'm not aware of any significant study who has provided a solution to this problem. And the problem is all of these like memory improvement models that have been proposed in the literature, most of them, like there are a certain number of researchers who work on these models, and most of them have focused on language learning. There are many publications by Duolingo, or there are similar, like Memrise. Memrise is another research group. They are a famous research group in London. They include like cognitive psychologists, deep learning experts. Like there are multiple specializations in their team, and most of them have focused on language learning. And there is something very easy about language learning, which is the flashcards or questions are disconnect from each other. Like there is no prerequisite relationship between them. Like if I've not learned that specific, like if I've not learned word A, I can still learn word B. There is no prerequisite relationship. However, in a college level course structure, we have prerequisite relationships, similar to like the relationships, the links that you see on One Academy between different topics, right? So there are two approaches to think about this problem. One is, what if we can somehow encode the relationships between topics from the syllabus of the course to enter our deep learning model? How to do that? I have no idea. We should think about it. We should come up with a solution. The other problem is, the other possible solution, as far as I understand, is what if we completely ignore the relationship between concepts? We train the model with multiple layers, and the model, because of having a lot of training instances, like training, like a huge training data set, the model automatically learns and embeds the network of relationship between concepts in the hidden layers. That is also a possibility. We should just explore to see, or maybe if any of you come up with a better idea, we can also explore that idea to see whether they work or not. Does this make sense to you? Do you have any questions? So our vision of this project, like the best case scenario, is that at the end of the day, we will develop a model to improve learning for college level students. We start with programming topics and we continue with other topics. So like the futuristic vision of this project is that if you're so successful with this project, at some point we can claim that using deep learning, like using machine learning, we are improving human learning in long run. Does this make sense to you?
Yes, and that's great if we would achieve this.
Yeah, but it's not going to be easy. That's why we started with a lot of literature review to make sure we understand what's going on in the literature before starting to work on the real problem. And what I'm going to do next week is that I'll make sure to create this anonymized data set and make sure everything is like well structured in the data set and understandable for you. I'll share that data with you, and we can just start exploring it to figure out what ideas we can try using that data set. Again, this is just going to be Python programming for like 4 or 5 or maybe 6 semesters. In each semester we have 200 students, but the number of data points is a lot. I don't remember exactly what number, but for every semester we have thousands of data points, because every time each student answers a question, and they do it a lot throughout the semester. So for every time they answer a question, we have a data point. And so we can start from here, and if we need more data, we have actually a huge data set that is coming. So no worries about the magnitude of the data. Any other questions? And you clearly understand why we need like a recurrent model like LSTM, right? Because it's about time. Like previous actions matter. Like the next recommendation depends on previous actions of this specific student and the topic.
Also can explore like the transformer model, which will try to like no, like pay attention to different parts of previous stuff.
That is also an option. Have any of you heard about bandits? Bandits?
No.
So that is
No.
also, have you?
No, yeah.
Yeah, so that is also another possible option to explore. I know a couple of papers who have used bandits specifically for solving this problem. Honestly, I feel like that doesn't work in our case. So there are certain like there are certain criteria and assumptions for bandit that I think are a specific problem. Like because of these prerequisite relations between topics, they are not independent from each other, and bandit's assumptions are not satisfied here. They're violated. That's why I feel like a recurrent deep learning model would be a better choice. But we can explore. There's no limit on what we can explore. Whoever can find a better answer here, we will have a paper. Any other questions?
I don't have any other questions regarding this topic, but I'm interested if we can continue proposing notes about some interesting deep learning models like generative adversarial networks, and also work on this research. I mean, I would like to do both of them.
Yeah, that is a question for you.
Oh, you mean doing two research at the same time?
No, I mean, I don't mean doing two researches. I mean like proposing some notes about deep learning, like deep learning,
Generalized
like
modeling.
yes, like connected with just knowledge and some concepts, and also doing research. Yeah.
Yes. Do you think that that can be a possible, maybe at some point that can help with the research topic we are now working on?
I think that might be helpful, and also that when I'm proposing notes and I'm writing, it also helps me to better understand some concepts, and that's helpful. But if it is not,
I think that is welcomed, but I think it's only when you have enough time, because you also need to, like, since we are working on a research, you need to devote time, I think first into the research topic like the deep reinforcement learning, and when you have time and you really want to share with about the generalized modeling, I think that is also welcomed.
yeah, of course, I understand that the priority of the research. Yeah. Thank you.
Is there any questions? Okay, so maybe that's all for our meeting today. I think that's a lot of information, and I'm looking forward to looking more deep into the field, and I think it's also a really meaningful and cool project to working on. So if there's no more questions, maybe we can just feel free to leave now.
Goodbye.
Bye.
Thank you.
Thank you.